Now, by now, we've spent so much time living in select statement land that we might have forgotten that databases can be created and we can create tables and add stuff to them. And we're finally ready to circle back and actually talk about that in great detail. So since the beginning of the semester, we've known that we've got these create statements and insert statements and things. And we've pretty much covered all we need to know about create statements for a table. There are a couple of things I want to talk about for completeness, but I want to go into more depth about the way insertions and modifications and removals work. And in service of that, I have, by the time you watch this, I have created a database for everybody on one of the servers. So we've got two database servers. For the sake of balancing out the load between them, you get your own personal database that you can do whatever you want with on one of them. And it'll depend on your student number. So it's been predetermined. And the idea behind this is that there's more to a databases course than select statements. Select statements are pretty important in life because odds are if you create a database, you are going to want to run a lot more select statements than insert statements or update statements or anything. But it's still really important to not only be able to design a schema like we've done in May, but also be able to actually implement it. And of course, there are a few loose ends that we have to tie up from May and early June, like all of these constraints that we were adding to our ER diagrams don't necessarily map naturally onto things like the table creation statement, like primary keys and foreign keys. So if you take a look at the Databases tab on Connix, it'll describe how you can access your own personal database. You are allowed to do whatever you want. You have complete access to this database. Nobody else has access to it. You can create tables. You can create stored procedures that we're going to talk about later. You can insert rows, update things, whatever. The usual rules apply, which is that it's a shared resource, so please don't abuse it. If we discover that your database is consuming too much storage or something, then we might clear it for you. If you begin pushing it, maybe we'll get in touch. But generally, do whatever you want. Try creating tables, try deleting tables, try adding rows and removing them. That's the best way to I guess, build the fluency that you're going to need. And more importantly, you've got this assignment on the horizon. And interestingly, the next few lectures are actually a build-up to this assignment 6, not assignment 5, which will be a compartmentalized thing, a written assignment that only covers some stuff that we're going to get to in early July. But assignment 6 is a project-style assignment where you're given a task, a very broadly specified task of creating a database and some Python programs that can query that database and add data to it. And you have to do everything. Everything is under your control. So what tables exist, how stuff is inserted into them, all of that is under your control. And so the lectures we're getting into now are building up to that project-style assignment. So what I want to talk about first, and that's easing in, moving from select statement land back to query to schema design land, is I want to talk about modifications. And in particular, I want to talk about once you've already created a database inside your DBMS, how do you do things other than just query the data or maybe add rows to your tables? And we want to pivot from there later into a discussion of, okay, so how do I limit the use of those operations? For example, if my database has constraints, like no student may have more than 2 majors or something like that, how do I enforce them? How do I make sure the database will never contain information that violates those constraints? So to be clear, what I want to talk about is the modification inside of a database. So you've already created the database. Now you have to add tables, drop the tables, insert rows, remove rows, whatever. It's worth considering, as I'm sure you've noticed, that our database server has multiple databases on it. And that there's a broader world out there of things like who gets to create databases, who gets to add users to the database system, and who gets to assign privileges. What does it mean to have permissions to access a database? For now, we're not going to talk about any of that stuff. We might have some time at the very end, although in a semester like this, I doubt it, to talk about things like the permission model. But our goal in a course like this is to talk about the internal database operations. So someone's created a database for you. And SQL doesn't really go into detail. The standard doesn't really explain how that gets done. Each DBMS has its own way of handling that. So Postgres, it's a pretty predictable create database command you can run. And MS SQL and MySQL and Oracle and SQLite all have different ways of handling how do we create the database, who has access to it. But then once it's created, we have to add tables and maybe delete them, maybe modify them. And so we're going to talk about that latter piece. So the main ones we care about, the main commands for the maintenance of tables are these ones: create table, alter table, and drop table. And these are modifying the global structure of a table. And we're going to discover that we don't care about these pretty much at all. We've spent quite a bit of time on create table. We're going to keep using it. We're not really going to need to use alter or drop table too much. We do run drop table commands pretty frequently. I mean, we every time we refresh our schema, we want to run drop commands, but we don't tend to use them except for a maintenance reason. An alter table, in a course like this, we don't have much use for it, but it's good to cover it anyway, because there are reasons in a database that already exists that you'd want to modify the schema. So remove a column from a table, or add a column to a table, keeping in mind that adding a column or removing a column from a table affects all of the rows in that table. What we are going to spend a ton of time on is the manipulation of the rows inside of a table. So we've already seen the insert statement, add a row to a table. The insert statement gets a little bit more complicated, but not too much, and it turns out most of our concern that we're going to have about the insert statement in the next few lectures isn't about how do we insert rows, it's about if I attempt to do an insertion, should it be allowed to succeed? And so we will tackle the insert statement that way. There is, of course, a delete statement that removes rows, and there's an update statement that allows you to modify rows already in the table based on certain criteria. Okay, so let's just talk about the table creation and alter statements, just for the sake of completeness. So here's the usual create statement that we've seen. And normally, of course, in an assignment, you'd be expected to add a primary key to this, maybe some foreign keys if needed. But the most basic create table statement might look like this. So it's got a list of columns and their types. And then I can insert a bunch of rows. Okay. There are these statements that allow me to destroy the table. We've seen that already, drop table. But there's also a number of operations you can do to modify the table while it's in existence. So one thing that we're going to put on hold and talk about later is this, whatever a constraint is, we'll define that later. We will talk in great depth about how to define those. But if we ignore the constraint issue for now, so a constraint is an arbitrary condition imposed upon the table. If we ignore that for now, we also have to do things occasionally like add columns, delete columns, rename existing columns, and we can see a couple of examples of the alter table statement here. So here I am altering the table that I created above, and I am adding a new column. We love that wonderful crisp SQL syntax there. Adding a new column called Z, and its type is real. So not too exciting in terms of the syntax. Also, I could run this rename column version of the statement to rename the column Y to YY or something. You can tell I'm not very enthusiastic about teaching this particular feature. So it's not terribly exciting to me that we can add columns and remove them from tables. It's worth considering that this statement here, given that the table already has data, so I could just sketch that out. So my table already has data, so 1.6, 1.7, 1.87, 3.70, -3, -6. So the question then is, if I have a table that looks like this and I add a column Z, well, wait, the column Z applies to every row. What do I do with this? So you have a couple of options here. It depends on your DBMS and settings that you're using and the type that you're using. But basically, your option is when you add a new column, either the column has to be defined for every row. So either every existing row gets a null value, or there are ways of providing that every existing row gets some default value. So the default value for a real number might be 0. But in any case, the column now exists for every row in the table if you add it. And that's all I have to say about the alter table statement. It's not, I mean, beyond the fact that it might come up in practice every now and then when you have to use it, it doesn't tend to be used that often. And so we'd rather spend time talking about manipulating rows. So here we are back at the traditional insert statement that we're so used to. We've spent a lot of time seeing this. I mean, we've sort of scrolled past insert statements a lot this semester. We haven't spent much time running it since early June or before then. But the basic syntax of the fundamental insert statement is this thing. So even if we ignore this, the nice multi-row version, if I want to insert a row into a table, I say insert into, in the table name, then values. And we notice that the keyword values has other applications. Values, then I just give the tuple that I want to insert. And of course, we know that we can insert multiple rows at a time. It's also, and as the slide is pointing out, the term values is actually not part of the insert statement. It's its own sort of operator that takes a list of tuples and then sends you back a relation that can then be inserted. And this is significant because it turns out that the insert statement really, what comes after insert into points 1 here, is just any relation, any list of rows. And as this slide points out, the values operator just takes your tuples that you provide and packages them up into a table form, and then insert into points 1 takes that table and dumps it into the table points 1. But it turns out you can provide anything you want in SQL that gives you back a list of rows. And one example would be a select statement. So if I want to, I can take a set of rows out of another table, a bunch of, like a combination of other tables, the result of a join, or some synthetic query that I construct, and I can dump those rows into a table using an insert statement. So here what I'm doing, if I do insert into points 2, the result of this select statement is first I run the select statement, and then whatever set of rows comes back, so I guess all of the points in points 1 where y is greater than or equal to 0, that gets inserted into points 2. So I can do that as well. The reason why that's helpful to me isn't necessarily that I want to spend too much time constructing tables out of other tables. You might think about this and realize that doing something like this in an actual database makes very little sense on a regular basis. Maybe when you're first constructing the data set, you might do something like this. But it doesn't make much sense to do this in general because the whole point of all of the goals we've had in this course about schema normalization and eliminating redundancy is basically that if you can get the data with a query, then don't put it in a table. Just use the query to get it. It's weird that you create a table out of data. So the fact that we can use a select statement inside of an insert statement isn't meant to imply that we need to do this a lot. It's actually just because a select statement gives us some flexibility that the traditional insert statement wouldn't otherwise have. And so just to clarify here, what goes after the word insert into points 2, this thing is a fully qualified select statement. And we've seen before that a select statement has lots and lots of components, one of which is the with clause. And so to be clear, because the select statement comes after this point, the with actually has to come sort of mashed between insert and select because it's part of the select statement, which comes after the name of the table. So that's a bit weird looking. It's not really inconsistent. It does make some sense. The reason why this is, and actually, okay, the slides are being cheeky here. So, okay, yeah, it turns out I can then mash the values clause into a select statement just to come all the way back around. The reason why this is helpful is that suppose that you've constructed an insert statement based on, I don't know, data you took from a user or something, and you would like to perform some pre-filtering using the database before you insert data into a table. You could always mix together this synthetic table that you usually construct, the result of a values clause, and the result of a select statement. So although this is a bizarre example where we're constructing a fake table with values and then just selecting everything from it, consider that, okay, so here's data I'm actually trying to input that somebody provided me. I want to manually insert this into the database. But because I've sort of contextualized it as part of a select statement, I can perform manipulations on it, like searching it or whatever, with the normal syntax before I insert it. And this might allow me, for example, to silently filter out invalid data if I want to do that. We'll see later that for assignment 6, there are cases where you want to silently ignore certain things, and there are other cases where you're required to catch them and produce an error if they occur. But for the silent ignore case, you could use a nested select inside an insert statement as one way of catching an error and this throwing it away before it becomes a problem. Because again, our goal ultimately is to make sure bad data never actually gets into our database. So one example would be, I could take the values that were provided, put them into a fake table, and then run a select statement to filter out certain things. For example, if I want to enforce that points 2 never contains x values greater than or equal to 7, I could make sure every insert that I do filters out any values, x values that aren't less than 7. And so we'll see later as we come closer and closer to assignment 6, which is due in August. It's due after the end of classes, so you'll hopefully have a lot of time to work on it. As we come closer to assignment 6, we'll see ways this can be beneficial. We'll also see reasons why there are parts of assignment 6 where it says don't do this. You have to enforce your constraint on the server side. If somebody's running this insert statement, we can't trust that they always put in the filtering, so the filtering should actually be done on the server. So here's an example of a way we could use our insert statement to avoid an error. Now, it's true that this has adverse effects in some cases, but suppose I've got this table students and I have this table CSE 370 students. Now, we wouldn't normally do this, but suppose I want to keep track of all my students, and then CSE 370 students has a foreign key constraint. And we should know that a foreign key constraint means that anything that I insert into this table here that has the foreign key, anything I insert, with the columns that contain the foreign key must exist. The values of all of those columns must exist in the table that they refer to. So if I say student ID in this table refers to student ID in this table, that means any student ID I insert into this table here must already be in the other table or an error occurs because referential integrity isn't being maintained. The foreign key doesn't properly reference the other table. Okay, so I try that. I insert into the students table these two student numbers. And then I want to insert some student numbers into my CSE 370 students table. And we notice that this one isn't in the students table. If I try, and you can try this insertion. You have your own database now. Go ahead and try it. If you try the insertion directly, it'll give an error. It'll say, I'm sorry, this student number doesn't exist in the students table. The insertion fails. And to be clear, if the insert statement fails, all of the insertions in the statement do not occur. So what I could do instead is I could say, okay, I only want to add the students on the list that actually are in my student list. So if you try and add a big list of student IDs, just discard anything that isn't in my main list of students. I don't care. Now, the reason why this is the example I use is I actually have this problem all the time when I'm working on marking or something in a course and it's like 3 weeks in or something. I try and upload the marks and Connex says, sorry, I can't find these 5 students anymore. And it's because they dropped. So I want to silently discard those marks because obviously if the students drop the course, the marking that was already done for them can be ignored. So what we do here is we take the student numbers I want to insert, we make them into a phony table, and then we join that table with students. And we know that the join will only send me back the student IDs that actually exist in the students table. And so if I do that, I silently filter out the invalid IDs. And so that's one way where in the insert statement, I can actually do some pre-filtering of my data, so sort of transparently before the data gets to the database. An example of where I used this recently, although not that recently because the IMDb data set's pretty old, but I used this a lot when I was uploading the IMDb data because as you may have noticed from assignments 3 and 4, the IMDb database is a bit of a mess. It's got all sorts of inconsistencies buried in there that aren't really the database's fault. I mean, the schema is consistent, but the IMDb data, the original input data was just not very good. It had a bunch of problems with it. And so this helped quite a bit just to get it into the database because IMDb's data, when it was uploaded, failed a bunch of foreign key constraints because it was so internally inconsistent. So we have also this delete from command that we can use to delete specific rows from a table. And as we know, a row has no identifying information besides the values inside of its attributes. And so if we want to delete specific rows, we can only really search for them based on attributes. I can't say stuff like delete row number 79 unless every row unless there's a column called row number or something. So in this case, if I want to delete from a table, the basic syntax is delete from table name where, and then the typical where clause that you'd see in a select statement. So any row that meets that criteria is discarded from the table. And we can, of course, throw in any arbitrary condition that we want. I could say things like order date is less than, and then if I want to compare two dates, I have to make sure that I put them both in date format, so the make date command can give me back a date. So order date is less than 2017. Any order from before 2017 is thrown away. I can even do nested select statements. And of course, the order of operations here is we do the select statement first, we take the result, and then we compare it to the rows of the order contents table one by one. And so I can do that, and the delete from statement deletes any number of rows. As long as the row meets the criteria, it's deleted. There's also this, so just like in the select statement, the where clause is actually optional. And so if you're not careful and you just run a delete with no where clause, this has the effect of deleting everything in the table. There's no where clause, so everything passes the condition by default. That really is sort of lousy when that happens, if you do that. There's one reason why often, of course, when you use database systems, you're not running queries on the database yourself. You've written programs that run queries on the database. But some people that like to live dangerously, administrators that like to live dangerously, occasionally do have to go into their database and run queries by hand. And this is a query you do not want to try running by hand. Delete from statements are the kind of thing you want to read it over 3 or 4 times before you press enter. And there have been great stories surfacing on the internet of, oh, today was my first day in my first job after graduation working on databases, and I accidentally cleared the entire production database for this startup that I work for. That's not fun when that happens. So the delete from statement, actually, if you're not careful, can delete everything. And even if you are careful, if you write a where clause that accidentally ends up being a tautology. So if you write a where clause that if you were to say something like order number greater than 1001 or something like that, maybe every order number is greater than 1001, you might end up deleting more rows than you expect. Fortunately for us, actually, if you use dbeaver, I noticed this while preparing for this lecture. If you use dbeaver and try this one, it doesn't let you. It gives you a warning. It says, are you sure? Because you're going to delete everything if you do this, which is annoying for me because I was actually trying to delete everything in the table in some cases. And so you have to keep clicking through a dialog box if you want to do that. The where clause of a delete statement is the same as the where clause of a select statement. You can put nested queries. You can have a chain of different conditions. You can use all the same operators. If you want, Postgres provides a couple of things that SQL, the general SQL standard, doesn't, and you're welcome to use those if you need to run delete statements on assignment 6. And then that brings us to update. So we've seen how to add rows, we've seen how to remove rows. What about if I have a row in there and I want to modify its value? So a pretty reductive way of thinking about this would be to say, well, I don't need a command like update. Why not just delete the row and add it back? I mean, if I have a row I want to change, why not just remove it and then add a new row with all the values that I want? You actually can do that in some cases. That often does work, but there are cases where that can have maybe unintended consequences. So a big one is it might be the row that you're working on. Somebody else might need it for something. The row, for example, could be referred to by the foreign keys of other tables, and deleting it could cause all sorts of grief. And so it's useful to have the ability to modify a row in place. So the SQL update statement, I don't know, from my end sort of annoyingly, the SQL update statement looks very different from an insert statement and a delete statement. It makes sense it can't be too similar to a delete statement, but it's quite annoying that you don't get one that looks like an insert statement, like an augmented insert statement. So basically the update statement is update and then name of table, and then this clause set, which gives a list of things to modify, and then a where clause that describes which rows to modify. So of course every row where the where clause returns true will be modified, and the modifications will be whatever's in the set clause, and there can be multiple columns. So I could modify 2 columns at once by separating them with a comma. So the first one would just go through and modify. If it finds order number 1001, it modifies it to 9999. Every row that meets that criteria, and there could be more than one, would be modified. And the second one modifies a customer's name based on the criteria being what was the order number. So we're changing the customer associated with an order. We're allowed to put nested select statements in both the set clause and the where clause. So for example, if I discover that people are trying to order pineapples and I want to put an end to that, what I could do is go find every row in order contents where the product ID is, oh wait, what's the ID of pineapple again? Actually, I don't care. I'll just look it up myself. I can just look it up dynamically in the middle of the update clause. And then I want to change whatever they ordered from a pineapple to a raspberry. So I look up the ID of raspberry with a nested select statement. Now, we have to be careful here. So we're slowly transitioning towards a discussion of constraints and constraint enforcement. We've already seen that there are ways in which constraints are enforced by default. So a typical one that you probably have already thought of or noticed is the primary key constraint. If a table has a primary key defined and you try to add 2 rows with the same values in all of the key columns, of course that doesn't meet the criteria for a key, the database will reject the second insertion. It'll take the first one. The first time you add a row with a given set of key columns, that's great. If you try and add a second distinct row with the same values in the key columns, it will fail. The operation will not succeed because the primary key constraint has to be enforced. The same thing holds with update statements and things like foreign keys. So if an update statement results in a row's in a constraint not being met on a row, on any row for any reason, whether it's a primary key, foreign key, or something synthetic, then the update statement fails. And if the statement fails, that's no fun, I guess, but we'll discover that that's a very powerful and useful technique. We like it when statements fail if they aren't supposed to execute. We don't want to necessarily define a path for handling the error. It's sufficient in many cases just to say, sorry, can't do this, and then expect the user to come up with an alternative themselves. So an update statement may fail if some rows come back, for example, if there is a row with order number 1001, and for some reason modifying the order number creates a problem. So an example would be if order contents has a foreign key on order number into the orders table, which it does in our database, every value in order contents, every row in that table, has to refer to a real order in the orders table. And so if there is no order called order number 9999, this modification will fail because the database will say, I'm sorry, I need order number to tie into the orders table, and this order number does not. So the update simply doesn't occur there. Keep in mind, you're allowed to issue an update command that in the set clause apparently does something invalid, as long as the where clause never passes. It's only if you attempt to actually modify a row that's impossible to modify that you get an error. Not if you have a set clause that makes no sense, as long as that set clause never as long as it's syntactically correct and never actually gets executed. Postgres, of course, provides the ability to use with statements on update commands, which is not apparently an ability in basic SQL. Basic SQL allows you to put the with clause on select statements, but not on update and delete, whereas Postgres does, which is nice. So where does that bring us? We've seen these commands, and a lower level course on databases would probably just stop there. Now you know how to update a database, and you know how to delete things from a database. What else is there to talk about? I mean, the reason that we care so much about these, the reason I'm bothering to discuss them and I've made slides about it, isn't because I think people need me to actually show them what the word update does in SQL. It's because we're going to discover that these are commands that are pretty easy to learn, and the reason we care about them isn't so that we can use them, it's so that we can prevent their use for invalid reasons. I just explained a case where the update command would fail because a row would be left in an inconsistent state. If there is no order number 9999, there shouldn't be anything in the order contents table with order number 9999. That would be an inconsistent state, so the database rejects that. What we want to build up to is the ability to program the database server dynamically for each database to add whatever constraints we need to make sure that our data is valid, that under no circumstances with any operation, whether it's an operation we expect to do or an operation that some third party might be able to execute manually, no operation should ever result in inconsistent data actually being added to the database. So any insert or update or delete that would result in an inconsistent state must fail. Now to do that, we're going to have to learn how to program the database server. We want to add basically our own code to the database as a database object, and that code gets run every time we try and add or remove or update a row. Now, before we can talk about that, we need to ease into this because it's going to look pretty hideous. Before we can talk about that, let's talk about how to define our own functions. And I'm doing this in a roundabout way because when you see the language that we have to use, it's this. Oops, this should say assignment 6. When you see the language that we have to use, PL, PG, SQL, with a name like that, you can tell it's going to be a fun time. The language is not as bad as it looks, but it does look really bad. So what we'll do first to ease into it is we'll talk about how do we define our own functions. And we've seen already that maybe all this time we've written all these SQL queries that are pretty complicated. Maybe the ability to define our own functions that we can then run all we want would have really helped us in some cases. And it turns out that the SQL standard does allow for database systems, and it requires, the database systems allow you to define your own functions, which you can then execute over and over again if you need to. Now, the key here is that the creating a function is like creating a table in terms of a DBMS. So on assignments 3 and 4, even if you knew how to create functions, you wouldn't have been able to because you're not allowed to modify those databases. So the reason we haven't discussed it until now is because until now you haven't had your own database to play with. So we're going to use the term stored procedure because, again, we're living in the 70s here. At some point in more recent taxonomy, people have moved away from the word procedure or subroutine to refer to these things. We'll call it a stored procedure. SQL provides this standardized mechanism for defining stored procedures, but for some reason no database actually implements it, as far as anybody can tell. Postgres is actually considered to be a very standard compliant database system. Like, it goes out of its way to implement the SQL standard, even parts of it that nobody ever seems to need. But even Postgres doesn't do this. So every database system has their own way of implementing user-defined functions. So we're not going to belabor learning a new language or anything. We have to use this weird language that Postgres uses, but we're only going to learn enough of it just to use it to write basic constraints. The learning outcome here is the ability to add constraints to a database, not knowing this weird, obscure, esoteric language. The reason why every database system has its own way of doing this, I think it's historical. It's because SQL didn't bother to formalize it until long after everybody had come up with their own system. So SQL apparently eventually defined this language called PL/SQL, which is a very weird, again, very 70s-ish imperative style language. And you might contrast, if you've taken something like CSC 330, you might have heard of things like PL/1 or something. Programming language 1, which you can tell that's the kind of technocratic term you'd come up with in the 70s if you thought you were defining the language to end all languages. So Postgres has its own specialized version called PL/PGSQL, which PG stands for Postgres. And to be clear, I still should say 6. To be clear, you will need to write some for assignment 6. And I'm going to post all sorts of examples that should get us around the headaches structurally. So you should basically end up just writing SQL and a couple of assignment statements inside of a function header that I've already provided. You will not have to write it on an exam. I would never do that to you, right? Exams might not be fun, but they're never going to contain this language. We will, of course, talk about database modifications and constraints on exams. We're not going to require you to write or read PL/PGSQL code on an exam. Technically, this idea of a stored procedure is called, this is a technical term that they use. I'm not going to use it. I'm just going to keep saying function or user-defined function or stored procedure. The idea basically is that if you want to program the database, what can you do? Okay, so one option would be you want to write a select statement that has certain behavior and you want it to be consistent. So an example being, you on assignments 3 and 4, you kept needing the primary name of a title for the IMDb database. And so you had to throw in the same subquery to your with clause every single query you wrote. Okay, but that's redundancy. We hate that in programming. We like writing functions if we need the same data over and over again. So instead of writing logic directly into queries, we want something a little bit better. So I don't want to do that. Okay, so what's the other end of that spectrum? The other end of the spectrum is to actually reprogram the database server. What I mean by that is the database server is written in C or C++. Go in and write your own C code and compile that into the database server. Okay, so that's not a good idea either, because obviously the database server runs lots of databases. You don't want to go write C code for every different database, recompile the whole thing. You want some middle ground. You want the ability to add your own custom-defined functionality to a specific database and to, of course, govern who is allowed to add it and who is allowed to use it, just like anything else in the database. But you don't want to have to write C code. You don't want to have to fall into the native code trap where when you're programming a database server, if you have to write C code, you have to begin worrying about stuff like, what platform is this database server going to run on? Well, that shouldn't be your issue. You should be able to connect to the server and know it's a Postgres server and not have to worry about anything else about it and be able to program it. And of course, the other problem with the native code trap is security, which is if you're writing, low-level C code, you could do whatever you wanted, within the permissions of the user running the database server program, which is pretty broad. You could delete all the files on disk or something, or all the files owned by that user. We don't want to provide the maintainer of an individual database with that level of freedom. We want their ability to run code that is scoped inside of a database and can't modify anything outside of the database. And so the notion of this persistent stored module in SQL tries to address that. So these functions that we create are, and we notice how, again, I call them functions, even though SQL calls them this thing, but the statement is create function. So even they're confused about this. The functions we create are basically the same type of object in terms of our database as a table. So I can add a function to one database and it won't be available in the other databases on the server. And of course I can create them and I can drop them just like tables. Now the reason that we care about this isn't actually because of the examples on this set of slides. I'm going through these examples as a sort of slow build-up. It's because we need these to write constraints. If we want to implement arbitrary constraints on the order of, if we're implementing a student database, every student can have at most 2 majors, or no more than 10 students can major in computer science, or something like that. Those are constraints that we would put on our ER diagrams for whatever reason. We need the database to enforce those. it turns out that the only way of actually enforcing such constraints in Postgres is by writing your own functions. And so the reason I have to teach this, even though I think it's useful for other reasons as well, the reason I have to teach it at this point is that we need it because it's the only way of getting our database to do what we want if we're using Postgres. So what I'm going to do in this video is just talk about the basic idea of these stored functions. So how do we get them to take arguments? How do we have them return values? We'll notice for constraint programming, we actually write lots of functions that don't take any arguments or return anything terribly interesting. But maybe this provides us some intuition into the data model used by these stored functions. So what is this weird language that we have to use? So the language we have to use is imperative. So it's similar to the style of language of C or Java or Pascal or something, which is a list of statements that you run in order, and you get if statements and loops and other things. The reason we need such an extension to SQL is that SQL as we know it isn't really an imperative language, it's a declarative language. A select statement, which is an example of an SQL statement, consists of a bunch of clauses that together describe what you want. So ultimately, a formal way of describing statements like, give me the list of all customers who placed an order that cost more than $25. So an SQL statement does not contain stuff like loop over the list of customers. No, we don't worry about that. We just describe a set of operations to perform that would give me what I want. And so for functions which need to perform a task using an algorithm, we can't use pure SQL. And so the idea behind this PL/SQL extension is to give us some imperative functionality if we need it. And so it turns out PG/SQL supports all the stuff we expect out of a typical language, including variables, assignment statements, loops, if statements, whatever. We're not going to need most of those things. We'll see a couple of them, but there's no use in learning them too much, although for the most part, if statements look pretty much like you expect them to. It's just there's some syntax peculiarities, but it looks like an if statement in any other language. What's great about this PL/PG/SQL, though, and one reason why we don't actually have to learn too much of it, is that you are allowed to write SQL statements anywhere you want in it. So I could assign a value to a variable based on performing a select statement and pulling a value out of the database, which means we don't actually have to learn that much about stuff like variables and loops because we can always have SQL statements do that stuff for us. On assignment 6, you're welcome to go learn more PL/PG/SQL if you want and use whatever features you need to. Okay, so here we are back at this schema again. And I'm going to do a separate video where I do sort of a demo of some of these functions that I'm writing here. So I would like to first write a function that takes the name of... So I've got all of these different products. Here they are. And some of these are delicious and some of them aren't. And I want anybody running a query to be able to easily distinguish about which products are delicious, which products aren't. Now, normally you'd want to keep a separate table of, is product number 3 delicious, yes or no? But fortunately for us, whether something is delicious is actually an absolute truth. Either it's this fruit, in which case the answer is yes. If it's this one, the answer is no. Otherwise, I don't know. It's one or the other. Who cares? So I'm going to write a function that returns a string. And it's going to be the string yes, the string no, or the string maybe. And you give me the name of a fruit, and I will tell you yes, no, or maybe, is it delicious? So the function looks like this. Let's just ignore this bit for now. So create function, and then I give the name of the function, and then I give a list of arguments like you'd expect. Fruit name, varchar. Notice that unlike other examples of the varchar type, we don't actually have to provide a length here, because the assumption is whatever field that somebody hands to me has already been defined, so its length has already been bounded. So you hand me a fruit name, and it's got this type, and notice that this doesn't look too different than a function signature in Java or C, except that the order of the types and the argument name is reversed, as you'd expect from SQL. The return type is specified right below it there. Returns varchar, and then some weird stuff happens. So the function's signature, in the sense that we're used to it from other languages, is this. Create function is delicious, returns varchar. The word as you might recall from the with clause, is to say, here is what the function is. So what's weird is that this is SQL, and so is this. But this is a different language. This is that PL/PG/SQL. And theoretically, other DBMSs allow you to write all sorts of weird stuff in here. I mean, theoretically, you could make it so you could write Python in here in some other DBMS. An SQL embedded function can be written in any language, theoretically. So the way you tell the database server that what you're about to write is a different language is you put some marker here And everything between this marker and the second occurrence of the same marker is considered to be the contents of the function. So I've been using I've adopted the convention of saying $body to say, okay, this is the body of the function. And then the PGSQL itself is this stuff. So between the statement begin and end, you can interpret those sort of like the opening and closing curly brackets. I have an if statement with a bunch of returns in it. So a very basic bit of imperative code. If the fruit name I was provided equals raspberry, return the string yes. Else if, so I don't know why we couldn't just say else space if, but for whatever reason we had to write it like this. I don't know why we couldn't have another E in there. Else if the fruit name is pineapple, return no. Else return maybe, and then end if. And we'll notice the idiosyncratic thens and the end if marker, but really, besides the sort of syntax, and that horrible else if, besides the syntax difference, this looks a lot like most languages you've seen already. And now I guess I should explain what's happening up at the top there. So just like a table, you've noticed in our the schemas that I've been posting over and over again for the fruit data, just like for a table, it might be this function already is sitting inside our database schema. And if I want to modify it or add it back to the database, usually for sort of general code hygiene, it's good to put a drop statement for your function right before the create statement. So drop function if exists. If the function is not already there, this does nothing. If the function is already there, it deletes it. If the function is not already there, it just does nothing. And that allows me to create it. Now, if you don't do something like this, if you don't have this line here and you run this piece of code twice, the second time the database gives you an error. It says, I can't create the function, it already exists, which is annoying if you want to modify the function as you go. Running this statement here, running this entire statement embeds the function into the database, and you can then use it. You can sort of view this like compiling the function and then storing the compiled representation into the database, although it's not like it's machine code or anything. It is parsed at this point and then stored in the database somewhere. Just to note, this marker has to be $signs, $2 with something between it. And then when you repeat whatever you put at the top, that indicates the end of the function body. Because it's the function body, I write it as body, but you could just do $, you could do code or something, as long as it's the same marker on the top and the bottom. So now that I've created the function, I can use it somewhere. Now, just like a table, you're not allowed to run the create function statement anywhere but a database that you have create permissions. So you may notice you can't create tables on our shared like Fairies 1 year database, just because that would be a bad idea. And so you can't create functions on those databases either. But you can create tables and functions on your personal database, so try this on there. So here's an example of a query that uses our isDelicious function. So once I've run this create function statement, the function becomes available for my use, and I can then call it like I would call any other function in the select statement. And there it is. So I would do this, and I'll have a separate video where I go through this and sort of show the progression through like what dbeaver actually does when you run statements like this. So this is, of course, a contrived example. Let's write a statement that might be something more interesting that we might want to use more often. So here is a quick function that uses some nested SQL. You'll notice it's actually performing a select statement and then returning that value, where I give you an order number. I'll call it the order num, and it's an int. And the function returns the total price of that order. And you already know, I guess, how to compute the total price of a particular order. I want any order whose order number equals the number you gave me, and then I just take the sum of the kilograms bought times price per kilogram of each item in that order, and then I return that. So I do the query to compute the price of the order, and then I return that. Because the return value is a real number, obviously I have to make sure that whatever nested query I'm performing inside of this has to return a single row with a single column. If it tries to return something else, we're going to have a bad time. This is nice because if you're using this database a lot and you often want the price of an order, you don't want to store the price of the order in a table somewhere because it's derived information. There would be redundancy if you did that. But you also may not like having to constantly do the join and aggregate that you'd otherwise maybe have to do to compute the price of an order. So this function gives you a way around that. If you want the price of an order, you now just select, for example, here I'm selecting the order number and the customer's name from the orders table. I don't even use the order contents table here. If I need the price of the order, I just call this function, which goes and gets the data from wherever it needs to come from. So that's one, maybe, hopefully that's proof that functions can be helpful. When you have permission to add them to your database, and once you've added them, anybody can use them. Now, it's true that just this one example is convenient, and in general, in a course like this, if it's convenient and it's valid SQL, go ahead and do it. But I have to observe that although this appeals to people who like the functional way of programming, so they like writing functions that do operations and things, they like batching up repeatedly used code into functions, and maybe they've spent all semester doing lots and lots of joins and aggregations and sort of felt that seemed wrong. Like we're doing lots of extra work having to constantly join and aggregate and write these massive queries. Keep in mind that every time you call this function, it's still doing a join and an aggregation operation. We're not really avoiding anything by calling the function. And actually, if I were to write this query all the way through, so if I didn't use the function, if I was going to select the total price of each order in the manner I might have done on assignment 3 or something with a big select statement, it might actually be faster because having it all in one big query allows the database's built-in optimization engine to maybe work more effectively. Now, it's hard to tell what an optimizer does, and in general, that means we shouldn't try and second-guess ourselves. If the function makes sense, we should use it. But there are reasons why performing the whole query in one fell swoop can often actually be faster, and that's one reason. If you were to run this query a lot and you noticed it was really slow, that would be a sign that maybe the problem, you want to do some profiling or instrumentation or something to see whether this was running slowly. So we've seen the basics of functions. I'll do a second demo video where I go through the SQL that I've shown in the lecture in dbeaver. And you may not need to actually write many functions of this form on assignment 6. You'll certainly have to write functions to actuate constraints, but you might want to write functions like this because they might be helpful to clean up your data set or to clean up your schema a bit, to make it easier to write queries. And on assignment 6, part of the assignment does involve writing queries to actually pull data out of your schema, and so you could find them useful for that.